Hello, everyone. I'm Julia from Krannich Solar. Thanks for joining our webinar today with SolarEdge. Before we get started, I'm just going to be giving a quick presentation about Krannich. Krannich Solar is headquartered in Germany and was founded by Kurt Krannich. Since being founded, Krannich has expanded into 23 different countries with the capability to ship to over 100 countries. Krannich has been a strong partner to PV installers since 1995 and offers everything that is required to begin and finish your solar installation. Our international purchasing power helped us build strong relationships with your favorite manufacturers, such as SolarEdge, to secure the best pricing and availability. With a growing market share, Krannich Solar is privately owned and a self-financed company that ranks among the leading solar wholesalers worldwide. Our experience in delivering solar products worldwide for the last 26 years has made us experts in our field. In 2005, Krannich expanded into the US with our US headquarters in New Jersey. We also have branches in California, Florida, and we are expanding into Texas with additional warehouses across the nation. We are growing every day, so keep an eye out for where we'll be next. Our US team consists of over 80 employees that service the Americas and strive to offer the best services and options to our partners. Throughout the years, we have grown our product portfolio to provide over 5,000 products. We've partnered with leading manufacturers worldwide to offer the best material for a project of any size, whether it's an off-grid system, 4-paneled shingled roof, or a megawatt flat roof. Working with Krannich means you'll never work alone. With our streamlined ordering process, each customer at Krannich receives a dedicated sales rep to walk them through each step of the ordering process, from project design to on-site delivery. The solar industry is always innovating and changing. At Krannich, we do our best to make sure you know about the latest products and technologies available. We team up with industry leaders and seasoned professionals to train you firsthand on everything you need to know, and it'll always be for free. And this concludes my portion of the webinar. Here is our contact information if you'd like to reach out for a quote or if you have any questions regarding the products or services we offer. And if you have any questions throughout the presentation, please feel free to ask them using the question box and we will answer them at the end of the presentation. Thank you again for joining us. And now I'm going to pass it along to Kleber and Jacob from SolarEdge.
Thank you, Julia. Appreciate that. Let me go ahead and get started here. I'm going to show, making sure that I'm picking the right screen. Jacob, good? Showing the correct one?
Yes,
All
sir.
right. All right, folks, good afternoon, good morning, good evening, right? I mean, greetings for everyone. Thank you so much for joining us. For the next 45 minutes, to an hour, we'll be talking about a very, I would say, timely topic in the industry with regards to UL 3741, which is a standard that started. I mean, that was actually started, like I would say, a few years ago, but it's something that just now is starting to get more popular. Okay. So we'll talk about the pros and cons, right? I mean, of using MLPs and not using MLPs, and recalling, we'll explain to you folks the DC optimization, and we'll talk, at the end of the day, right? Like the agenda, as I mentioned, is that we're going to give a quick overview of the solutions and also the standard, as well as we wanted to present an economic comparison between solutions with and without a DC optimization, and that's going to be the two topics for today. Okay, so to get started, I'll go ahead and just do a quick introduction. So my name is Kleber Facchini, Director of Techno Marketing for CNI for North America for SolarEdge. I've been with SolarEdge for close to 2 years, but I'm not new to the solar industry. I've been in the solar industry for close to 15 years. And so I've seen ups and downs in this industry, and I've seen enough. Okay, so I've seen a lot. So I'll let pass Jacob, if you'd like to introduce yourself.
Yeah, hi everyone. My name is Jacob Faber. I'm a field applications engineer at SolarEdge. I have 4 years of experience in the solar industry and a little bit longer doing teaching and training of all sorts. And I'm based in Denver, Colorado.
All right. Thank you, Jacob. So I'll go ahead and get started. I'll start with the first part of the presentation, and then Jacob is going to, I'll pass the baton, and Jacob will start do the second part of the presentation. Okay. So like agenda, I think I already talked about the agenda. So the agenda is understanding a little bit overview of the standard, SolarEdge solution, other solutions as well. We're calling the non-DC optimized solution. And then we'll talk about the benefits, right? Of using DC optimization, which is the solution that SolarEdge uses. So really, and as Jacob is going to say, right? That we have done this study with the help, and actually, with Pure Power has reviewed the methodology, has reviewed the numbers. As Jacob is going to mention, that we believe, that this is something that we can stand behind the numbers that we're going to show. Okay, and the numbers that we're going to see here, it's going to be available in a white paper that we're going to be releasing in the next week or so. So this is a summary. The presentation that we're doing here is a summary of the white paper that we're going to be releasing in this very topic. Okay. So just a quick thing about SolarEdge, right? So #1 solar inverter company in revenue. Okay, we had about $1 billion revenue in Q2 of 2023, and we have like we talk about optimizers, right? Close to 120 million optimizers shipped today, and 48, close to 50 gigawatts, of shipped worldwide for customers, a variety, Fortune 500, 100, globally, worldwide. Okay, so just to start, right? For the folks that are not used to our system and to our platform, I would like to provide a high-level overview of the SolarEdge solution, which is based on the integrated DC optimization, the DC optimizers, which means that the inverter and DC optimizer are tested in the factory, and that we, right, SolarEdge, are responsible for the system and not only for one piece. The system has been evolving since first deployment, and several advancements have been introduced to that propel the industry forward in cost optimization, energy production, increasing safety, and streamline O&M of the plant. Okay, just like to list a few, right? Increase in energy production, because of the optimizers, we're doing panel level and PPT, so reducing the effects of shading and module mismatch. Longer strings, fewer strings, right? Providing flexible design, reduction of balance of system, and enhanced safety via the safe DC technology that brings the voltage down to 1 volt DC at output of each optimizer, and module level monitoring, so we call like continuous and granular monitoring, because you're monitoring what's going on at the panel level. Okay, so all of the benefits that Jacob is going to explain later is because of the use of DC optimization. Okay, just a quick thing here is a reminder for everyone, right? Like this is our lineup, our 3-phase C&I lineup with inverters, smaller inverters, right? At 208 and 480 volts, right? 10, 17, 3.3 kilowatts at 208, 40 kW at 480. And then also we have for larger applications at 208 volt, 50 kW, and at 480, 80, 100, 110, and 120. Okay, if you folks need more details, we'll gladly get you more depth, but and also data sheets are available online. And just one thing here, I want to show this is so this is a Synergy, our Synergy platform, Synergy inverter. That's for the larger applications, for rooftop large applications. And one thing that we have all the benefits besides pre-commissioning, right? Besides surge protector devices, monitoring of terminal blocks from a temperature perspective, is that I want to highlight the single DC input functionality, which actually we presented in the spring, for Krannich here. It is a single DC input that allows savings on balance of system, and that's something also that Jacob is going to be introducing and explaining the fact that we can put everything close together at a centralized location. Okay. On the optimizer side, so SolarEdge launched last year DC optimizer with patented and proprietary Sense Connect technology. Okay, this technology automatically detects and prevents potential electric arcs at the connector level rather than just the string level. With the ability to detect abnormal changes in connector temperature, the Sense Connect this technology constantly monitors power optimizer connectors, identifying improper connections and possible malfunctions. Okay, and once that's detected at abnormal temperature, voltage is brought down, to 1 volt, brought down to a safe voltage level. Okay, so in other words, this is designed, right? I mean, to catch issues before it happens, before it develops to like potentially like even fires, right? I mean, electric arcs. So this is why we have. I mean, this is important, I mean, to have the Sense Connect and to have this technology that we have in the S series optimizers that is already available to order from SolarEdge. Okay. So now I'm going to launch a quick poll. Okay. Let me see if I can go ahead, if I can navigate this. Okay, so let's see here. Launch. All right, here we go. So are you considering using solutions without MLPs for rooftop applications? Those would be the solutions, right? That are under UL 3741. So I'll give like a minute or so here. Okay. And then again, I mean, those I've seen folks saying, yes, I'm considering, other folks so no, and the others saying, I'll never consider, you know what I mean? So that's interesting. I mean, I'd like to understand, you know what I mean, where the audience here is in and what you're considering so that we can gauge, right? And then we can also have a discussion. And again, folks, we're trying to have an open debate, you know what I mean, about all of the new trends, the latest trends on that. Okay. All right. I'm going to, I think folks voted here. All right. So I'm closing. Let me share. Okay. So I think I'm sharing that. And poll results attends the app. So if we're considering, so 58% yes, 31% no, and 12% I'll never consider. Okay, good. So it looks like that majority of folks know what we're talking about. So that's great. You know what I mean? That's the good audience. You know what I mean? That for us to present this. Okay, let's see here. I think I'm also showing my screen.
Kleber, we're still seeing the poll.
You're still saying the poll. Okay, so how about now?
There we go. That's better.
Perfect. Yep. Thank you, Jacob. Appreciate it. Okay. All right. So just starting with from a standard perspective, just like doing like a quick recap. So the white paper that I talked about that actually Jacob authored that goes from the NEC from 2014 all the way to 2020. But let's start from the 2020, right? I mean, for the sake of time. The 2020 National Electrical Code offers different options for rapid shutdown compliance regarding conductor control inside the array boundary. So upon rapid shutdown initiation, right, I mean, those are the options. The system, right, must accomplish less than 30 volts within 30 seconds within the, outside, right, I mean, the array boundary. And inside of the array, that's where the options come. So less than 80 volts within 30 seconds using a 1741 listed PV rapid shutdown, or the listed or field labeled hazard PV control system as per 3741. So that's where opening allowed, you know, for 3741 systems. Okay. So the introduction of a 3741 standard for photovoltaic hazard control in 2020 was hailed as an important milestone in the solar industry's continuing driving to improve solar system safety. Building on rapid shutdown best practice first introduced in the 2014 code, and it was conceived to equip the solar industry with more options to accomplish compliance to rapid shutdown in PV arrays, with the primary objective being to protect firefighters when dealing with fires in buildings with solar installations. In this respect, UL 3741 has achieved a notable success. I think that's right. However, the concerns that we're going to be showing here are arising regarding the safety of some of the PV hazard control solutions that have entered the market since the regulation's introduction. Okay, so again, the issue here is not 3741 that we're going to be explaining, it's the systems that are coming to the market, right? And also how that's being certified. Okay, so just as a quick introduction, so 3741 and also IEC define hazard levels. This is a graph for hazard levels based on protection electric current that can flow through the body when a person falls into array. For example, fall into array, right? I mean, with a tool, a sharp tool. As voltage increases, as you can see here, right? I mean, so I mean, you can see from voltage, array voltage DC, milliamps, right? This is a more or less of a it's a different table from what we see in 3741, but we're attaching voltages to it. Okay, as voltage increases, more current can be pushed through the body, and hazard levels above 1 per the are not allowed in the array without additional protection for firefighters. The additional protection could be either voltage reduction or physical or mechanical measures. Okay. As I'll explain later, SolarEdge's maximum optimizer voltage of 125 volts DC results in about 30 milliamps, remaining within hazard level 1 range, so no additional protection is required. But solutions without MLP, which keeps the array at 1,000 volts, right, even after rapid shutdown, results in around 460 milliamps, well beyond the chart. So this is why, I mean, the folks always ask, so do we need extra protection like the UL 3741 racking? We do not, because our system, like I explained, stays within hazard level 1. Cool. Okay, so let's quick look here, I mean, at our solution, the SolarEdge solution, right? How it works. So DC optimized systems, which is a system with DC optimizers, right? I mean, that I'm showing here with inverters, allow for 2 panels to be connected in series, meaning that upon rapid shutdown initiation, the maximum voltage within the array is 125 volts DC. So that's the open circuit voltage of 2 modules in series. As a result, the systems fall within hazard level 1 or lower inside the array boundary, eliminating the need for additional protective measures to comply with 3741. 3741 compliance is built within our optimizers and inverters, require no extra parts. This solution, referred as DC-optimized, consists only of optimizers and inverters and can be used in combination with any PV module and any rack. The solution maintains design flexibility with no need for special racking, raceways, wire management, guards, module combinations, inverter collocation, etc. So that's design flexibility that we call that. Jacob will explain later on. So what that means, right? And I'm showing here like a quick picture of the array, the voltage level. So upon a rapid shutdown, as soon as there is a rapid shutdown event, majority of the voltage levels in the array is going to be at 30 volts DC or less, right? I mean, the output of the optimizer, the string level is going to be 30 volts DC. Within, I mean, the output of the optimizer, 1 volts DC, and like I mentioned, right? I mean, you still have 125 volts DC at the combination of 2 panels. So that's the maximum voltage that will be seen in the array. Okay. So now let's look at the other solutions, right? I mean, what we call the non-DC optimizer, right? I mean, so 3741 opened the door to allow solutions that use few, if any, MLPE devices to be code compliant, okay? In these solutions, AC conductors are de-energized using traditional string inverters, okay? However, the DC array itself is kept at high voltage levels, 1,000 volts, even after a rapid shutdown is initiated, corresponding to hazard level 3, okay? To mitigate this risk, UL 3741 states that solar arrays need to be made safe and not allow any exposure to dangerous voltages during firefighting interaction. This means that every wire, module, or energized component in the array that can be accessed during firefighter operations must be protected from damage using robust wire protection measures, such as sturdy wire guards and conduits. It is at this point that some of these alternative solutions start to lose traction, and that's kind of where we would like to open the eyes for everyone here. This is not to any flaws in the 3741 standard itself, but rather it is because of the way it is being interpreted by some manufacturers and certification agencies. Okay, as you can see here, some solutions using cable ties, right? As everybody knows, cable ties will break, after a few years. Okay, and this is actually something that I've seen, in the field. I went to like an application where new installation, everything is connected, everything together, right? And then after 2 years, cable ties start to fall off, right? And that's the biggest concern, right? In non-DC optimized systems without integrated rapid shutdown, that accessible live wires with voltage levels up to 1,000 volts are held in place by nothing more than plastic cable ties or plastic raceways. So from day one, those exposed live wires may pose a significant risk to firefighters or workers, and that risk will only increase as normal wear and tear, including sun exposure, snow, and wind, potentially causing the plastic ties and raceways to deteriorate. Okay. Once this happens, more sections of conductors may become exposed, accelerating the shock hazard risk to firefighters. Furthermore, the likelihood of arc faults and ground faults developing into fires is increased as the array will be maintained at 1,000 volts even during array or inverter faults. Okay. And again, this is not putting just firefighters that go up in the roof, right? I mean, with like protected device, but O&M personnel and asset managers, should be extremely concerned that with some of these solutions here, field crews will have to work around 1,000 volts instead of hazard level 1 voltage levels. And the hazards of an accidental short or broken module can be exacerbated by the 1,000 voltage level present in the array. Okay, so that's something that we've seen in the field of kind of plastic cable ties, wire, and also wire race plastic ones, falling off. So just to summarize here, I'm not going to read through, but here's kind of like the quick summary between systems without DC optimization or without MLP and system with DC optimization, right? Is that without DC optimization, electricity or voltage is always capped at 1,000 volts as long as the sun is shining, right? I mean, you have, if there is a problem with the array, or that's what we call like it's a fail-safe system, there's an installer that's not fail-safe, right? Dependence of other components, like I explained to you, hazard level 3, right? I mean, requires other protective measures in the array, right? And compliance inspection, right? I mean, so this is something that if you use this optimized solution, you don't have to be doing this. But with non-DC optimized, you're going to have to be doing this compliance, check later on in the future. And safety, like I explained, safety beyond firefighter protection, for instance, for O&M workers, is just allowed with the systems with DC optimization. Okay. So with that, I'm going to run our last poll here. Okay. So let's go ahead and do, now let's start getting into the economical benefits. Okay. Oh boy, I think let's see here. So let's keep going. Unfortunately, I pushed, I cannot relaunch the poll, but I pushed, like the sharing the results too quickly. But anyway, let's go ahead and get started. Jacob, I'll pass the baton to you so that you can go over your presentation.
Thank you, Clever. So yeah, I'm gonna move a little bit away from the safety and the compliance discussion and talk a little bit more about the dollars and cents here. So, it might make sense to expect that removing MLPEs from your rooftop is a big opportunity for cost saving. And what we wanted to do is take a little bit closer look at that claim. And what we've done is taken 5 typical rooftop C&I PV systems of various size, and we looked at 2 design variations to be UL 3741 compliant. And obviously one of those variations is using the SolarEdge DC optimized solution, and one using a non-DC optimized solution. So we did 5 of these case studies. We had 3 of these systems undergo an independent review and verification by Pure Power Engineering. And we use the same approaches for the other 2, and those approaches for simulating production and estimating balance of system costs, etc. Those approaches were also validated, independently by Pure Power. So I want to skip, basically right to the headline here. What we've determined over 5 different case studies is that savings on balance of system are pretty consistent across the spectrum. There's up to, and some cases even over, 50% savings on balance of system when using a DC optimized solution. Obviously, the big question is why. So this typical reason that balance of system is reduced using a SolarEdge system is that we allow for much longer strings. We can go up to 60 panels in a single string, where traditional string inverters might allow only 16, 18, up to 20 maybe panels per string. And that's going to lower the string count considerably, which is going to lower your DC cabling costs. However, when we look, that savings reason is going to apply to almost any system, C&I, ground mount, at different sizes. But when we look at a comparison against non-DC optimized racking solutions that are 3741 compliant, there are a few additional reasons that balance of system costs are going to increase. So the first one, if we go to the next slide, is design flexibility. That's kind of at the heart of cost increases here. Traditional string inverters need to be installed within 1 foot of the array to be 3741 compliant. This means that you can't really install your inverters together at a centralized location or at the ground level on systems that are larger into the 200 or 300 kilowatts or greater size. This is going to mean increased AC balance of system costs because your AC cabling runs are going to be more expensive, often need to be oversized to keep resistance losses low, and they're just going to be much longer. On the other hand, with the SolarEdge DC optimized solution, you can install your inverter at centralized location or even at the ground level if that's what's desired. And you can use aluminum cabling from the DC combiner box side to further cost reduction. So I want to show an example here of why inverter placement is important, as well as the use of PV rapid shutdown equipment. So this is a look at a rooftop array about 2 megawatts in size. This is a 3741 non-DC optimized solution. And you can see that the inverters are distributed throughout the array so that they are co-located to the modules that they're connected to within 1 foot of the array in each case. Due to fire code requirements that, there need to be setbacks, there need to be walkways, you're almost always going to have subarrays in a rooftop system like this. And the way to remain code compliant when using a non-DC optimized system is the use of PV rapid shutdown equipment, listed PV rapid shutdown equipment. And that can take a couple of different forms we'll talk about a little bit more later, but you can see those are also going to be distributed throughout your array to maintain compliance throughout this for the entire system. When we compare that to a DC optimized approach, first of all, there's no requirement to use PV rapid shutdown equipment because the hazard reduction is occurring at the module level with MLPEs. As well, for that reason, inverters can all be located centrally, near to your AC switchgear or your grid interconnection. And so when we put those two systems side by side, we can see that AC cabling from inverter to combiner and from combiner to interconnect is going to be much more expensive in both material and in labor for a non-DC optimized solution. And when we have done an average of this across all the case studies, we've estimated that the AC cabling, conduit, grounding, and install labor account for an increase in 4 to 5 cents per watt on your balance of system costs. So another consistent reason for balance of system cost increase is the specialized racking. The SolarEdge DC optimized solution is basically agnostic to the racking that's used, doesn't require any special racking to be 3741 compliant. However, the listed racking solutions that are not DC optimized use a number of accessories that limit exposure to high voltage cables, often between rows or between columns of the PV array. And as well, they have special accessories to maintain gaps between those cables and any metal on the PV frame or the racking structure. So there's a couple images up on the screen here that show examples that exist in the market of how those mechanical protections need to be put in place for 3741 compliance. And this also translates to additional cost of labor and equipment for all of these extra components, if it's cable ties, if it's covers, etc. And so again, when we see an average across all of the case studies that we performed, the estimated material and labor cost addition for these accessories is about 1 to 1.5 cents per watt, depending on your system. And finally, the other piece that we're seeing consistently have an effect here is the requirement of MLPEs or PV rapid shutdown equipment to maintain NEC compliance. So it is sometimes possible to avoid the use of these devices entirely, but it is quite rare to have a C&I rooftop without some breaks in the array, given the necessity for fire code walkways, rooftop obstructions, and other reasons that rooftops aren't perfect for us when we're designing systems. So one option shown on the screen is to use PV rapid shutdown equipment, listed devices, whenever strings cross the gap between subarrays. So you can see in the image here, this is a contactor combiner box. 1 to 2 of these devices is needed per subarray. And the other option for NEC compliance is to use MLPEs on some of the rooftops, so not every module, but for any module that is connected to an inverter in a different array or a different portion of the array. So the image here shows how modules that are connected across a gap between 2 portions of the subarray are all going to require some type of RSD at the module level. If you'll go forward, Kleber, I just wanted to highlight where the strings are crossing gaps in the array. And so any module connected to those inverters is going to need to be connected to MLPE. And so when we look at the average increased cost for using MLPEs or PVRSC, there's a variety of strategies. Over 5 case studies, we're seeing an average cost of 0.5 cent to 1 cent per watt, strictly on the MLPE or PVRSC side of things. So back to the big question, the big elephant in the room. BOS savings are great, but do they really make up for the cost of MLPEs? And we use a market research average of 7 cents per watt for inverter equipment, and we got that's a number from NREL. And what we did is put together a final estimate of all capital expenses. So that's your price of equipment, both MLPEs when used and inverters. That's balance of systems, direct labor. And what we're seeing is that these systems using DC optimized solution or non-DC optimized solutions are similar in cost. But in fact, non-DC optimized solutions are actually more expensive in 3 of the 5 systems analyzed. So obviously there's some variance here. We see variance depending on how cookie cutter the array is on the rooftop, what strategies are used for 3741 compliance. Systems are closer and further in CapEx costs, but it's quite close, and the difference may well be in favor of using a DC optimized solution. So that's CapEx. We want to also take a look at Opex costs for a system throughout its lifetime. If DC optimization is not used, additional tasks and costs are introduced for a project. And we've discussed with various O&M providers to try and come up with a list of the additional tasks that are necessary for a system that doesn't have continuous and granular module level data. So one of those costs is IV curve tracing. This is used to debug issues when there are production problems in a PV system. With the DC optimized approach, you're getting data real-time, web-based monitoring of your production. So using this type of practice is not necessary. Most often we would expect this type of issue to occur in the commissioning phase or at the end of life. And as such, we've modeled it using a bathtub curve. And same goes for infrared scanning and connector inspection. So this is if arcing or ground faults, are noticed at some sort of site, instead of for example, in the SolarEdge optimizer solution, we have the Sense Connect feature that Kleber mentioned earlier. And the Sense Connect feature is going to cease inverter operation and lower array voltage automatically if connector issues occur. And so there's no need to do infrared scanning or visual inspection to figure out where there are issues. Again, this is expected to happen more often in the early and late stages of a system life, so it's modeled with a bathtub curve. Drone inspection is something we've heard is typically done annually for this kind of system. An annual inspection for array safety compliance. So to maintain compliance with the standard, given wear and tear and aging of mechanical components, if we want the system to still provide benefit to firefighters, frequent inspections for robustness of these mechanical protective devices should be done. And this is another operations cost that we are expecting for systems that are using non-DC optimized solutions. And finally, without granular monitoring data that you get from each optimizer in your field, on the rooftop, there would be more likely to require truck rolls if investigating issues in the array. And there's more time spent on site finding those issues because you don't know down to the module level exactly where an issue has occurred. So all of these costs added together, we're modeling that over a 20-year lifespan for a PV system. And we're estimating that just under $60,000 per megawatt, that's in net present value, would be added cost to a system that doesn't use a DC optimized solution. So if you'll go to the next slide for us, Kleber, you can see that when we include those costs, the Opex costs for non-DC optimized systems, the overall system cost is going to lean even more heavily in favor of utilizing DC optimized solutions. And I just want to say that this is an estimate of additional Opex costs for non-DC optimized solutions. It's not that there are no Opex costs, obviously, for a DC optimized, but these are the additional costs that we would expect. And finally, we want to look at a comparison of energy production. So all PV modules experience some degree of mismatch. Can we go to the next slide, please? Which cause potential power losses and can drag down your overall system performance. So this is common in all types of solar panels, and even more common, or bifacial panels are even more susceptible. And it happens for a variety of reasons. If it's shading, if it's soiling, if it's microfractures on one module versus the next, just differences in manufacturing. And in traditional PV systems, the loss of production on a single module in a string is going to affect the ability for that whole string to produce power at the maximum level. When you're optimizing at the module level, as you would with a SolarEdge system, only the module affected by, if it's soiling or shading, is going to be reduced in production. And so this mitigation of mismatch effects will lead to less losses throughout the system lifetime and a higher production of energy throughout the system lifetime using DC optimized solution. So again, what we've done is run energy analysis via PVsyst, and we look at a year 1 and a year 20 analysis of energy production. And can we skip to the next slide, Claudia? And again, our simulation methods have been independently reviewed and validated by Pure Power for this. And when we see the delta in production, from years 1 through 20, we can, using estimates of utility rate for that energy, annual escalator, inflation rate, we can get a net present value estimate for the increased energy revenue that is going to come from that additional production using a SolarEdge DC optimized solution. And for those 5 different projects, you can see the average is about 7 cents per watt in net present value over 20 years. And so when we add that into our overall cost compared graph, if we treat expected energy revenue as an offset to system costs, we can see that the economics for DC optimized solutions are even more preferable because over the entire system lifetime for system owners and stakeholders, it's going to be a lot cheaper. So I want to summarize all of the things we discussed today, and then we'll move on to the Q&A. First of all, first point, number 1 for us is safety. Using automated and engineered protections to remove hazards, as we do with the DC optimized solution, is safer generally than using passive mechanical components to hide hazards. On the balance of systems side, up to 50% savings is possible on the balance of systems. It's by reducing number of DC strings, decreasing the length of AC cables, and avoiding the use of additional accessories for hazard control. You can increase energy revenues by up to 5% over the system lifespan, reduce O&M costs by leveraging our web-based real-time monitoring at the optimizer level, and finally, generally having more design flexibility. So, inverters can be installed at centralized locations at the ground level, which allows for shorter AC runs. And the array can be broken into many subarrays to avoid obstacles on the rooftop, and you can maximize rooftop space without the concern of having to add additional PV rapid shutdown equipment or hazard control accessories. With that, I think it's time to open up the floor and answer some of the questions that have been posed here.
All right. So thank you, Jacob. I think everybody, so we're back here. I have a few questions here from the audience. So the first one is, does UL 3741 apply only for commercial installations or also residential? So that was Santiago. So yes, Santiago, so it's for both. So 3741 is for both commercial and residential.
Yeah, and I'll just add on that, we don't see the use of racking solutions to UL 3741 typically on a residential project, but it does apply. Yeah.
That's right. Okay, so let's see here. Next one. Are you saying, and that's from Susan, are you saying other UL 3741 listed systems are not safe. No, Susan, we did not say that, and we actually, that's very clear. We did not say that the other systems are not safe. However, we wanted to open the floor for debate, right? I mean, so we wanted to show the differences, and we want to also show, I mean, like the only thing that we want to say, like Jacob said, is that whenever you have a system that has its 125 volts DC, whenever there is a problem, right? I mean, it's a safer system, you know, that we have 1,000 volts. So, and I'll let the audience, you know, me to make the judgment here, but we're not saying, by any means, we're not saying that the other systems are not safe. Let's see here. For the hazard, yeah, so for the hazard control system, does the racking also need to be listed, or is the fact that SolarEdge equipment is listed as a hazard control system sufficient? That's correct. So for SolarEdge, if you're using SolarEdge, because like I mentioned, like previously, if we are using SolarEdge solutions, the maximum voltage is 125 volts DC. So that's what I showed in that modified table, right? I mean, from 3741. So the system is 125 volts DC, and it yields less than 40 milliamps, and therefore there is no need for extra equipment. Okay, so that's why, and actually we're going to be releasing a paper, not a paper, just like an app note, a short app note on that, because there are some HJs asking that. And so because we are hazard level 1, we don't need extra equipment to comply to NEC. Jacob, do you have anything to add?
No, I think you covered it pretty well.
All right. The other one is it mandatory to use SolarEdge inverters with optimizers for ground mounts? So at this point, yes. So we believe in our topology, we believe in architecture. So for the ground mount version, yes, it's used with optimizers, DC optimizers, and we just released a large 330 kW inverter for community solar applications, ground mount, and it's also with optimizers. Okay, so let's see here. That's a good question. I don't know if I'm going to know this, but how is UL 3741 being implemented or acknowledged by the insurance industries in the cost assessment for a policy, especially here in Florida, with a limited amount of underwriters willing to include PV systems in their coverage? So it's a good question. I don't know the value. However, I can get you one thing that publicly, FM Global, it's a worldwide company that does insurance, and they require optimizers for the systems that they're going to cover. Okay, and we are also talking with another insurance company that I cannot disclose, but yes, there is also they're also going to start requiring, DC optimization, especially with the Advent, right? The 3741. So, but I cannot. That would be something that it'll be actually an idea for another webinar. That would like to kind of present that with an insurance company. Do you think that wire management racking systems are not important for safety overall? I'll let you, Jacob, chime in on that. But in my opinion, yes. For me, yes. Wire management, it's important. All we're saying here is that wire management, as anywhere and anything, right? It especially whenever you do, like you use a cable tie, or like you use plastic conduits, right? Or plastic wraps. That that kind of equipment, you know what I mean, tends to wear, tear, and it tends to break. So then you can make the judgment: 125 volts DC, 1,000 volts DC. Jacob, I'll let you chime in.
Yeah, I would say the same thing. It's not that, I wouldn't say it's not important. The question is how important, and are the wire management systems critical to avoiding exposure to 1,000 volts DC, or are they, or is the, maximum exposure level 125 volts or lower? At that point, the wire management is still useful, still important, but it's not critical for, reducing hazard exposure.
Agreed. Okay, let me see if there's any other questions here. Okay, so I actually have one more question, Jacob. If we go back to this slide here, right? I mean, where you kind of did the punchline. So just that there's a question here. If this comparison here includes, excuse me, everything, including the optimizers, does it include all of the equipment, including the balance of system?
This is CapEx costs entirely, including inverters, optimizers, optimizer or MLPEs if they're used for the non-DC optimized solution, all of your balance of system costs, direct labor costs. That all goes into the analysis of capital expenditures, everything up until the moment you turn the system on.
Mm-hmm. Very good. All right. And I also wanna, I don't think there are any other questions. So we'll finish here. Just one slide, you know what I mean, that from a resources perspective, right? I mean, we have on this topic, we have done 3 webinars with industry experts and also with customers, right? I mean, like VP, first one was with EDPR, second one was a solar landscape, and also with a firefighters and code experts. And we have an article, right? I mean, that we have released on PV magazines and Solar Power World, and that's what we're showing here. And we're also the white paper that's about to be released in the next week or so. Okay, so that's going to be also an email that we'll send to everyone, and that's going to go into more details, right? I mean, what Jacob and I just presented here. Okay, so with that, I'll turn it over to Julia.
Awesome, guys. Thank you so much. That concludes our webinar for today. If you have any more questions, please don't hesitate to reach out. Thank you again for joining, and have a great rest of your day.
Thank you all. Bye-bye.
Bye, everyone.